Welcome back to Space. Exploration has always represented the pursuit of the extraordinary and the unknown. Starting from the launch of the first satellite to the exploration of distant planets, humanity's venture into space has consistently pushed the boundaries of technology. Now, one of the most revolutionary technological frontiers on the horizon is quantum computing. This vital field has the potential to reshape the landscape of space exploration, unlocking new realms of possibility in space-related research and technology. However, in an unexpected turn of events, NASA has decided to put the brakes on its ambitious quantum computer project. This decision is causing ripples in the scientific community following a series of developments that have cast a shadow over the future of the intriguing intersection between AI and quantum computing. Coincidentally, this issue is something that many prominent figures in the scientific community, including Michio Kaku and Elon Musk, have been warning about for years. Due to their immense power, quantum computers can potentially crack any known digital code. This poses a significant threat, as it means the crown jewels of any nation, containing top-secret military and defense information, could be vulnerable to advanced cyber threats. The concern over the potential misuse of quantum computing power has led to calls for government oversight. With the ability to breach data centers and access critical intelligence, the implications for public safety are apparent. The danger lies in the unforeseen consequences or dangers lurking within the realm of quantum computers, prompting the sudden shutdown of NASA's quantum computer project. Join us as we delve deep into the importance of quantum computing, exploring the real reasons behind NASA's decision to pause its quantum computer project and the potential consequences that prompted such a significant move. Quantum computing, a field that combines the principles of quantum mechanics with computing power, has ushered in new frontiers in science. One of the most captivating ideas within this realm is the potential to simulate the entire universe using quantum computers. At the core of this concept is the Schrödinger equation, a formula utilized by quantum physicists for almost a century to describe the behavior of particles like electrons and photons. In contrast to the observable world around us, where objects have clear positions and speeds, quantum particles exist in a realm of probability and potential. The Schrödinger equation aids in predicting the probable locations and behaviors of these particles. Now, envision using this equation not just for a single particle, but for every particle in the universe. This is where quantum computing comes into play. Quantum computers operate on qubits. Unlike the bits in traditional computers, qubits can exist in multiple states simultaneously, a property known as superposition. Coupled with other quantum phenomena like entanglement, quantum computers possess a unique ability to handle vast amounts of information. This capability raises the prospect of simulating the intricate interactions of all the particles in the universe. The motivation behind simulating the universe is multifaceted. It could serve as the ultimate test of our understanding of physics. If we can create a virtual universe that mirrors our own, it would signify that our physical laws are on the right track. Additionally, such a simulation might offer insights into currently elusive questions such as the nature of dark matter, the behavior of black holes, or the origins of the universe. However, the idea of using quantum computing to simulate the entire universe is both audacious and complex. Let's break down why this is such a monumental challenge. Quantum computing represents a radical departure from traditional computing. While classical computers use bits that are either 0 or 1, quantum computers use bits that can exist in a state of 0, 1, or both simultaneously. This ability to exist in multiple states allows quantum computers to process vast amounts of data simultaneously. Nevertheless, simulating the universe with its unfathomable number of particles and complex interactions poses an astronomical computational challenge beyond the current capabilities of quantum computers. The Schrödinger equation, a cornerstone of quantum mechanics, calculates the wave function of a quantum system over time. This wave function provides probabilities of where particles might be and how they might behave. In theory, applying the Schrödinger equation to the entire universe would require knowing the wave function of every particle and all the forces acting upon them. While this equation is powerful for predicting the behavior of particles, its application to simulate the entire universe is a formidable task due to the sheer scale of calculations involved. The aspiration to use quantum computing for simulating the universe is a grand challenge, both in terms of computational feasibility and the intricacies of applying quantum mechanics to such a vast and complex system. The exploration of quantum mechanics raises intriguing questions, as it inherently deals with probabilities rather than certainties. When applied to something as massive and complex as the universe, these probabilities become intricate. Additionally, the Schrödinger equation, a fundamental tool in quantum mechanics, assumes that quantum states evolve in a smooth, continuous manner. However, in the real world, particles often behave unpredictably, experiencing sudden jumps from one state to another, known as quantum leaps. This unpredictability poses a significant challenge for any simulation based on the Schrödinger equation, as accurately predicting these jumps remains beyond our current understanding. In summary, while the Schrödinger equation provides a powerful tool for understanding quantum states, using it to simulate the entire universe is a task of unimaginable complexity. It involves not only computational power but also a deep understanding and accurate application of quantum mechanics principles on a universal scale. The interpretation of quantum mechanics plays a central role in the idea of simulating the universe. Quantum mechanics, fundamentally dealing with probabilities and uncertainties, differs significantly from the deterministic laws of classical physics. One well-known interpretation is the Copenhagen interpretation, suggesting that a quantum system's properties exist in a superposition of all possible states until measured. This raises intriguing questions in a simulated universe, particularly regarding the collapse of quantum states during measurement. Another interpretation is the many-worlds interpretation, proposing that all possible outcomes of quantum measurements are realized in separate universes. In a simulated universe, this implies an exponentially growing number of parallel simulations, each branching out with every quantum measurement. The computational complexity of such a scenario is unfathomable. Additionally, the role of entanglement, where particles can be connected in a way that the state of one instantly influences another even over vast distances, adds another layer of complexity. Entanglement challenges our understanding of space and time and would be a critical factor in any universe simulation. In contemplating the nature of reality, these considerations underscore the intricate challenges and philosophical inquiries that arise when attempting to simulate the vast and complex universe using the principles of quantum mechanics. In a simulated universe, the distinction between the virtual and the real blurs, leading us to a philosophical and scientific crossroads regarding the nature of reality. The concept of simulating the entire universe prompts questions. If a simulated universe is indistinguishable from our perceived reality, what sets the real apart from the simulated? This notion is reminiscent of Plato's allegory of the cave, a philosophical thought experiment questioning perceptions of reality. In the context of a simulated universe, if beings within it perceive their world as real, who's to say it isn't real for them? This contemplation aligns with the simulation argument put forth by philosopher Nick Bostrom, suggesting that if advanced civilizations can create simulations indistinguishable from reality, it's probable we are living in one. A simulated universe also challenges our understanding of consciousness. Would entities within the simulation possess consciousness? And if so, what does it imply about the nature of consciousness itself? Is consciousness a physical phenomenon tied to the brain, or is it something more abstract that can emerge in any sufficiently complex system, even a simulated one? Furthermore, in a perfect simulation, entities within it might never realize they are in a simulation. Their laws of physics, history, and understanding of the universe would all be defined by the simulation parameters. This scenario raises profound questions about our own reality. How do we know we aren't in a simulation ourselves? In summary, the idea of a simulated universe not only pushes the boundaries of quantum computing and physics but also delves into the realms of philosophy and consciousness, challenging our fundamental understandings of reality and existence. In other words, this quantum leap in computing power has the potential to revolutionize various fields. NASA, in collaboration with Google, has made significant strides in exploring the possibilities of this cutting-edge technology. To illustrate the rapid progress, Google's 53-qubit Sycamore computer and IBM's 433-qubit quantum computer showcase the remarkable capabilities. The pace of advancements in this field is indeed remarkable. However, recent developments have thrown a curveball into their cosmic aspirations. The U.S. government, expressing concerns over the swift advancements in quantum computing, took an unprecedented step by requesting NASA and Google to hold their quantum computer projects. This decision has left the scientific community bewildered, considering the potential benefits quantum computers could bring to space exploration, cryptography, and other technological fields. Prominent figures like Michio Kaku and Elon Musk, who have long warned about the dangers of unchecked developments in both AI and quantum computing, find themselves echoing their concerns. Kaku, a theoretical physicist, emphasizes the risks of AI surpassing even nuclear warheads, while Musk highlights the urgent need to regulate AI development. The decision to halt NASA's quantum computer project raises questions about the interplay between AI and quantum technology. Could there be unforeseen consequences or dangers lurking within the realm of quantum computing that prompted this sudden shutdown? One major concern is the potential threat to encryption systems. Quantum computers, with their immense computational power, can break traditional encryption algorithms, sparking alarms about the security of sensitive information, including financial records and classified data. This poses a potential risk to military and civilian secrets, not to mention the secure transactions vital to the global financial system. As world powers vie for the first-mover advantage in the quantum computing realm, the term quantum supremacy takes on geopolitical significance. This raises worries among prominent figures about the potential implications. Michio Kaku acknowledges the government's keen interest in advancements in this technology, particularly the CIA. Government agencies are already issuing statements urging people to be prepared and make changes in their behavior. Because when this revolution is in full swing, all secrets could be accessible to even a next-door neighbor. While we may not be at the point of worrying about this technology every day, the implications are significant and warrant careful consideration. But it's inevitable. There is a significant need for the development of practical quantum computers in the coming years. While classical computing has made remarkable advances in recent decades, there are still many problems beyond the reach of classical computers. Even parallel computers do not offer the same exponential speed-up that quantum computers provide. Quantum computing opens up a promising avenue for solving problems and unlocking new applications in scientific and technological advancements, ranging from cryptography to material science. As Michio Kaku aptly stated, Mother Nature is quantum mechanical. The universe is, in some sense, a quantum computer. This implies that quantum computers will enable us to perform chemistry without chemicals. Everything from batteries to vaccines, currently invented through trial and error, could be accurately simulated with quantum computers, eliminating the need for bubbling flasks. Quantum computing holds the key to unlocking the secrets of various phenomena, from human aging to photosynthesis, which occurs as a near 100% efficient quantum process at room temperature. Kaku envisions groundbreaking possibilities, especially in material domains. For instance, the century-old Haber process, consuming 2% of the world's energy to produce fertilizer, could be revolutionized by quantum computing, ushering in a new green revolution. In the medical field, quantum computers could analyze drug mechanisms at a molecular level, model and test new drugs without human trials, and sift through vast data sets to identify emerging pandemics. On a cosmic level, quantum computers could predict and model asteroid strikes, solar flares, gamma-ray bursts, and other celestial threats. They could also unravel the mysteries of the universe, such as the life cycle of stars, stable fusion reactors, and the enigma of dark matter. Kaku emphasizes that quantum computers are indispensable tools for solving physics problems beyond the capabilities of digital computers, including the mind-boggling Planck energy and the mysteries of dark matter. In Kaku's optimistic view, there seems to be no human problem that quantum computers won't be able to address. From unraveling cosmic mysteries to solving challenges on our planet, maybe even the last step in finding the theory of everything.